This next one was done during my quantum mechanics class for a final project as part of the explanation. So here we have two light rays. The frequency at which they're rotating represents the frequency of light. Um, they're both the same frequency in this case, although they're colored differently just to distinguish them. Um, so you saw them rotating. They were rotating at a constant rate from the beginning. I'm just going to restart it here so you can see. So they're both rotating at a constant rate. One is entering this slit up here. The other is entering this slit down there. And they go towards the Y position of the mouse cursor on the screen. And when they land, they have a certain orientation. The red one landed in that orientation at that spot, and the blue one with a slightly different orientation. So then I add them tip to tail, as you can see, to produce that white vector. And the square of the magnitude of that white vector, scaled down by some constant factor, is then plotted to the right as a distance from the screen. You'll see what I mean. So as the white arrow gets shorter, it gets closer and closer to this line, right? And as it gets longer, now it gets longer. And this actually shows, it reproduces the outcome of the double slit experiment, which is interesting because, well, this had to do with Feynman's QED book, the quantum electrodynamics. He talks about um, this stuff and talks about how the photons will take both paths, and then there's a probability amplitude associated with each one, or there's an amplitude associated with each one, the blue and the red arrows, and then you add up those possibilities so they interfere with each other, and then take the magnitude of the result and square it to get the probability of observing the particle at that point. And if you go to the double slit experiment, you'll see curves like this, although it depends on how many or how far apart the slits are and how far away the screen is from the slits. But you see this interference pattern where there's a lot of light here because it's tall in this direction, and then there's nothing here, and then more here. You get this distribution. And I can also adjust the number of slits because that's fun to like maybe 6. And then there are 6 slits, and there are going to be 6 different ones coming in. I just think this is kind of cool to see. So they're all rotating. They all land at different orientations, which affects what the resulting sum will be. And then you can plot it in exactly the same way. And in this case, see how it just looks like one monomodal or unimodal, or however you say that, one lump here in this distribution. And as you increase the number of slits more and more, yeah, it just becomes like one peak, which is what you would expect with non-quantum mechanical effects. So this shows that when there's just a huge gap, then things behave as you would expect more classically in terms of the wave entering and appearing on the screen. Thank you for watching.